Okay, so in this lecture we will start talking about topological vector spaces. Okay, topological vector spaces. Okay, so as the name suggests, we will be starting with a vector space, or in fact, this is analogous. We can also start with a topological space as well. But I am talking about a vector space to be starting with, just because it's I would say it's a less rigorous structure as compared to a topological space in some sense. But rather you can also talk about starting with a topological space itself, because after all we will be eventually trying to do the same thing. So we start with a topological space, okay, or a topological space or a vector space. And so suppose if I start with a vector space, I want to endo V with a topology, okay, with a topology. Now I am obviously assuming you know what a topology means, so I'm not going to get into the details. And if I am somehow starting with a topological space, then I want to give it, so I want to endo a vector space structure, but can I eventually endo it with any vector space structure? That should be an obvious question. That is, provided you have a topological space, can I just provide any vector space structure? Because there can be numerous ways of appointing a vector space structure to it, right? And most of those ways should actually carry no link to the topology, to the already existing topology. And a similar question might arise in case of the vector space itself, that if I start with a vector space and I try to endo a topology on it, then I can have certainly many ways to do so. But in most of the cases there might arise some complications, because the topology might not be linked in any sense to the vector space, right? So when we are trying to endo two structures, two geometric or two algebraic structures on the same space, we are always careful about whether they go well with each other or not. For example, when we start with groups and we endo an additional operation on a group to form a ring, which I guess we have all studied, then we are always careful about the fact that both of these operations go well with each other, what we call the distributive law. Recall, in rings one of the axioms which needs to be obeyed is the distributive law, because we are always careful about the fact that when there are two or more structures on a same space, then we are always careful about whether these structures are some sort of interlinked with each other, or they go well with each other or not. So we'll have obviously an analogous notion of how can I endo a topology on V such that these two structures, the vector space structure and the topological structure, they go well with each other. And a similar case will appear here as well. If I somehow start with a topological space and I try to endo with a vector space, I need them to sort of collide with each other in a very simple way, okay. But before coming to that, I will obviously want to set some notations, and just for completeness, let me formally define what a vector space is, okay. I hope all of you guys know what a vector space is, but it's still for completeness, because we are discussing both of these notions. Let me give definitions of what both of these notions formally look like. So an additive abelian group V is called a vector space over a field F if the following conditions hold. If the following conditions hold, right? So what should be the first condition? That for all alpha coming from the field and vectors coming from capital V, alpha times V, alpha multiplied from the left, that is the usual convention. This is inside the vector space V. So this operation is somewhat somewhere defined outside these properties as a separate operation called the scalar multiplication, but rather it won't cause any difficulty because we are independently assuming V to be an additive abelian group and we are considering field separately, so we can do it in some sense of property itself. So this is called the scalar multiplication. So what I am trying to say here is that the scalar multiplication is closed in V. Okay, the scalar multiplication is closed in V. And the second property is that the distributions hold with respect to the scalars. Scalars are typically called the field elements. With respect to the scalars as well as with respect to the vectors. Okay. So for all alpha 1, alpha 2 coming from F and V coming from capital V, then alpha 1 plus alpha 2 V, so is basically multiplying V with the scalar alpha 1 plus multiplying V with the scalar alpha 2. Similarly, for all alpha 1, now I have a multiplicative operation on F itself, so I want to link it also with the additive operation in V. So if I have this, then alpha 1 alpha 2 scalar multiplied with V is same as alpha 1 multiplied to alpha 2V. Now you need to be able to distinguish between when what operation is being acting like this is the usual scalar multiplication, right, and this is the multiplication of multiplication in F. Okay, you need to be careful about when what operation is being considered. Okay, and that's, I guess that's quite trivially observed. Okay, right. Number 4 is that now the distribution holds in terms of the vector space itself. So if alpha is a scalar and I choose two vectors v1 and v2 from V, then alpha times v1 plus v2 is equals to alpha times v1 plus alpha times v2. And lastly, the scalar multiplication by the element 1 just gives back the vector itself. Okay, so these are the properties of vector space hold, and in fact these properties needs to be existing in order for a additive abelian group with respect to a field to be called a vector space. And our usual notation is this Vf. So this is what we mean by V is a vector space over F. Okay. Now there are numerous examples. For example, any field is a vector space over itself. Any finite direct products of fields is a vector space over itself. For example, Rn is a vector space over R. Cn is a vector space over C. Right. Then I have also a fine vector space structure concerning the group of matrices. So I know that the collection of all n cross n matrices over R forms an additive group. So in fact it's an additive abelian group. So it also forms a vector space over R. I can also consider this to be an additive to be a group over C, and then it will form a vector space over C. And all these properties are pretty easily verified. So you can verify it on your own, or I guess you have verified it in some point of your mathematical studies. Now what a topology is, so let X be a non-empty set, or rather let X be a set itself. Then a subset of the power set of X, that is a collection of subsets of X, is called a topology. Is called a topology on X if number 1, that the set itself and the empty set are there in tau, if we have an arbitrary collection of elements from tau. If let's say u alpha such that alpha comes from some indexing set lambda is an arbitrary collection of elements from from tau, then the union is also in tau. The union of all these u alphas is also in tau. Okay, so this is what we call that tau is closed under arbitrary union. Okay, so you need to keep in mind that tau is closed under arbitrary union. Number 3 is that, so I am just simply writing it in words, that tau is closed under finite intersections. That is, if I choose a finite collection of elements from tau, then their intersection will also be in tau, and we are only considering finite here, not arbitrary. Now, in very simple sense, for example, a vector space is sort of a generalization of the usual vectors in your 2-dimensional or 3-dimensional Euclidean spaces, which you have studied in your school level. In a similar sense, if you have studied metric spaces or if you have studied real analysis, you know that open sets follow all of these 3 properties. That is, the whole space is open, the empty set is vacuously open. If you have an arbitrary collection of open sets, then their union is also open, and if you have a finite collection of open sets, then their intersection is also open. So topology in some sense is a generalization of open sets. Okay, and that is the reason why we call the elements inside a topology to be open. So we have used this convention, used this notion of an open set to be simply an element of a topology. So any element inside this topology tau will be called an open set in X. Okay, and what should be usual examples of topologies? So you can consider the collection of all open sets in the real line, in any arbitrary metric space, and there are some non-trivial examples as well. So for example, there is something called a co-countable topology. We are not going to get into those details until required, but I guess you guys should have some sense of a topology. I guess you guys have studied some sort of topology in some sense, right? So in this case, we say X, this pair X with tau is a topological space. Okay, and if you choose any element from tau, then we say that U is open in X. So this is just a conventional sense. Okay, so for like in metric spaces, we start with defining a metric on a set, and then we define with using those metrics that what should an open set be. In a topological space, the whole discussion starts with open sets itself, and every other notion depends directly on open sets itself. Whatever you study in a topological space are completely dependent on open sets and nothing else. While in metric spaces or in your simple Euclidean spaces, we start with a metric or a norm or something like that, which defines sort of distances or lengths of vectors. In those cases, we use those tools to define what an open set is, right? So it's some far more general notion, I would say. Okay, right. Okay, so now throughout this series, we'll consider a vector space over either a real field or a complex field. Okay, these two will be only our topic of discussion. Now we will set some notations first. Now we are slowly guiding ourselves to our main notion, but it will take a little bit of time, I guess. Notations. So let X be a vector space. So whenever I say X is a vector space, I mean it's a real vector space or a complex vector space. And A and B are coming from X, and alpha is coming from the underlying field, which is real or complex. Then we define, how how do we define? Okay, so we define x plus or minus a to be the set x plus or minus small a such that small a comes from capital A. Okay, and this is done for all vectors x in capital X. Okay, number 2, we define the sum of two sets to be the set A plus B such that A comes from capital A and B comes from capital B. And the last is we define the scalar multiplication of a set as the scalar multiplication of each individual element. Right. Clear? These three will be essentially required over and over again. Now something to be immediately observed is that by the way we define these notions, the set 2a, 2 times a, is not equal to a plus a, though it looks to be same. Got it? So okay, via these conventions. Why is it so? So this is quite easy to prove. See, in fact, we can show that this set 2a is contained in a plus a. Observe that let x be an element from the set 2a, then I can write x as 2 times a, therefore x is some 2 times a where a is in capital A, but 2 times a can be written as a plus a such that a is in capital A, and clearly every element in a plus b is of the form, or rather every element in capital A plus capital A is of the form sum of elements coming from A. So these two are, both of these are elements from capital A, so this implies that x must be an element of A plus A itself, right, which essentially implies that 2a is contained in A plus A. But conversely it's not true. Why is it not true? Because since A plus A is the collection of elements of the form A plus B such that A comes from capital A, B comes from capital B, therefore if I choose an element A plus B coming from a capital A plus capital A such that A is not equals to B, then this element cannot be inside 2A, because elements inside 2A are of the form 2 times A, so it must be of the form A plus A. Since A and B are not equal to each other, it cannot acquire the form 2 times A or 2 times B. So this cannot be in 2A, right? So therefore A plus A is not contained in 2A, so it diminishes the equality. So it's a one-sided inclusion. Okay, right. Now we will define two very important notions which will again come over and over again and again. So see definition. Okay, so we are having a vector space X over a real or a complex field. I am not writing that over and over again. So a subset C of X is said to be convex if Tc plus 1 minus T times C is contained in C, where 0 less than equals to T less than equals to 1. Or what do I mean by this? So I think you guys have a very vague notion of what convexity is. So let me just give a diagrammatic representation first, and then I'll explain how this definition occurs. There's nothing complicated in here. So if I choose, so suppose I say this is a space X and it's convex. That means that if I choose 2 points from here within X, then the line segment joining X and Y, okay, so that's not exactly how a line segment looks like, but still. So line segment joining X and Y, this must be entirely contained inside X, right? This is entirely contained inside X. Okay, that is what is the simplest notion of a convex set. So if you carefully observe this exact thing via the notations which we previously gave, this simply makes the sense that so C in X is said to be convex if Tx plus 1 minus Ty is contained in C for all xy in C and T acquiring the range 0 to 1. That means whenever I choose two distinct points, or rather 2 points, if I choose a single point, there is no concept of a line segment joining it with itself, obviously. So if I choose two distinct points x and y, then the line segment joining x and y is completely contained inside C, right? So it sort of abides by our usual notion of convexity. So in this case, we say that this subset is a convex set. Okay. The next definition is also quite important. B in X is said to be a balanced set if alpha x is contained in B for all x in B with so rather I should write it in this way, for all x in B, rather let me define it in this way, that it's said to be a balanced set if for all x in B, alpha x is in B for all alpha in F such that the magnitude of alpha is less than 1. Okay, less than or equal to 1. Clear? Got it? Okay. So what is it trying to say is that, suppose this is my set B inside X, and I choose an arbitrary point X from B, then if I scalar multiply X with some alpha such that the magnitude of alpha is less than or equal to 1. Now alpha is in the Euclidean space R or C, so we have an obvious notion of magnitude. We simply know, notes down its distance from origin or the length of the vector it represents. So then alpha of x is also inside B whenever mod of alpha is less than or equal to 1, or alpha comes from the closed unit disk of R or C, right? Fine. The other way of representing the same thing is that alpha B is contained in B for all alpha in F such that mod of alpha is less than or equal to 1. Clear? So in this case we say it's a balanced set. Okay. Some quick examples. Let X be the vector space C over C itself. Then observe that C and the empty set are balanced sets. Okay. Now phi, the empty set is a balanced set vacuously because there is nothing inside phi, so there is no notion of talking about anything, right? And C is a balanced set because whatever scalar we are picking out, it's getting multiplied to the element of C itself, right? So it immediately follows from the closure of multiplication in C because C is a field, obviously. Another notion, but another balanced set which is quite important to observe is that all open or closed disks centered at origin forms a balanced set. Why is it so? So the proof is quite simple. So let me just show it for the open set. It will obviously hold for the closed set in a same analogous sense. So let B be the set B0 epsilon, where epsilon is a positive number. So we are considering an open ball centered at 0 and radius epsilon, and if I choose some element x from B, then we know that the modulus of x must be less than epsilon, right? Now what is the modulus of alpha x? So it is modulus of alpha times modulus of x, but modulus of alpha is less than or equals to 1. So this is less than or equals to modulus of x, but modulus of x is less than epsilon, right? Therefore the distance of alpha x from origin is still less than epsilon. So alpha x must be immediately in B. So B is immediately a balanced set, right? Okay. And a closed set will be the same thing. You can easily observe it from here that if I have do not have a strict inequality here, then I won't have it here. So it's obvious. And the next important example is if I consider the vector space R2 over R. Now you need to keep in mind something, or rather I am just giving a note of it. We know that R2 is topologically same as C over R, if you recall, right? Because over R, so the basic thing is that, or rather I do not need to actually introduce the notion of R, sorry, because we are talking about topological. So R2 is topologically the same as C, because you can immediately recall how the complex numbers are geometrically interpreted, and how in a two-dimensional plane the usual coordinates are interpreted. So you can immediately observe that they are actually topologically analogous in some sense, but vector from the vector space point of view they aren't, right? They are not isomorphic or equivalent in terms of topology. So now the immediate sense why this isn't the case, because what should be the dimension of C over R? So it's 2, right? Dimension of R2 over R is also 2. So this somewhat links towards an isomorphism may be existing, but let's see. So what are the balance sets in R2R? Okay, actually the balance sets are much more geometrical or much more deep rather than simply in the complex field, because you can observe that in R2 over R, a line segment with center at origin is also balanced. Okay, a line segment with midpoint 0, 0 origin is balanced. Okay, why is it so? Let me just give a diagrammatic representation. So you can actually prove it down yourself mathematically, but there's not actually it's very simple to observe. So suppose this is a line segment with the midpoint to be the origin. Now if you choose any point, here up here, let's say this is a point xy, and if you multiply it with some scalar whose length is less than or equal to 1, it will just drag down this point somewhere closer to origin. And similarly, if you choose a point here, so the vectors will be just get dragged down towards the origin, right? It will just get dragged down towards the origin, but it will remain on the same line segment, because whenever we are choosing 2 points from the line segment and we are multiplying it by alpha, so alpha acts as just a scaling factor which decreases the length of the vector from origin. Okay. So try to analyze the fact that whether this can help us in in some sense as a way to base the fact that the complex numbers and the two-dimensional Euclidean space are not equivalent in terms of vector spaces, or rather try to examine that R2 whether it's isomorphic to C as a vector space. Okay. Now it can be a non-geometrical equivalence as well. Okay, you can show that the geometry of the vector space structure of R2 may not be equivalent to the vector space structure of C. Rather, we will take this up in the next lecture, obviously, but for this lecture, let's keep it as an exercise. Okay. Now, some important notions which we will be eventually taking up over and over in terms of topology. Let me just give them one by one. Okay. So, okay. So some topological notions. Okay. Let X be a topological space. let X be a topological space with respect to the topology tau. The number 1, these are the things I think you should know, but rather let's keep it here. So U a subset of X, or rather let me not use U, E a subset of X is closed if and only if its complement is in tau, that is its complement is open. Number 2 is that the closure of E, so we will keep so we will keep this throughout the properties. The closure of E is defined to be the intersection of all closed sets which contains X. So C is closed and E is contained in C. Okay, so this is what we call the closure of E. The closure of E. Number 3, E interior is defined to be the union of all the open sets which contains E. So U is open and U is contained in E. Okay, so this is called the interior of E. Now if you have studied real analysis or metric spaces, you have obviously studied some different definitions for the closure of a set and for the interior of a set in terms of interior points, closure points or limit points, but eventually you can actually try and prove that these two notions are equivalent, that is containment of all closure points and a set having all its elements as interior points. These sort of notions of the definition for interiors and open sets, interiors and closures and so on and so forth, they are actually equivalent to this notion as well. So whatever the definition you have studied for a closure of a set in case of metric spaces or in case of your real analysis, you can see that that's actually equivalent to defining the closure to be intersection of all closed sets containing E. Okay. There is also a sequential definition of closure of a set, but that will also come out to be equivalent to this. Okay. You can try and prove it on your own. Clear? Then we say that number 4, this topological space X tau is said to be Hausdorff if for all x not equal to y in X there exists disjoint open sets UV in X such that X is in U and Y is in V. Okay, so what does a Hausdorff space mean? So suppose you have this as your topological space and you choose 2 points X and Y from X, then you can always get 2 disjoint open sets. So you will get, for example, this to be a disjoint open set from here. So these are 2 open sets. So let this be U, let this be V. Okay, you will always get 2 disjoint open sets, one containing X and the other containing Y. Like for example, metric spaces are always Hausdorff. Okay, metric spaces are always Hausdorff. What can be or how can you say that a metric space is Hausdorff? You can actually see it from this diagram itself. That is, if you take the distance between X and Y, you reduce it to its half, then you can find 2 balls centered at X and Y separately which do not intersect. Try and do it on your own. I gave you the idea of how to do that. It's very simple. Okay. Right. One importance of a Hausdorff space is that in a Hausdorff space, all convergent sequences have unique limits. Why is it true? I'm again giving a hint towards it. Why is it true? Suppose you have a sequence which converges to 2 different limits. Suppose xn converges to X and it also converges to Y, and suppose we presume that X is not equal to Y. But what does convergence means in sense of a topology? It means that after a certain point, every element of the sequence xn is in every open set of every open neighborhood of X. An open neighborhood, you can simply think of it any open set containing x. Okay, so after a certain point, every element in the sequence will be contained in every open set containing x, and the same thing will happen for y itself. That is, after a certain point, every element of the sequence will be contained in every open neighborhood of y, right? But if this happens, then we will always get two neighborhoods, one of x and one of y, which intersect at one of the points in the sequence, right? Let me give a brief description what I am saying, that if xn converges to x, this means that there exists some n1 in n such that n greater than equal to n1 implies that xn is in U for all open sets U containing x. Now this can also be thought of as a sequential the definition of convergence in a topology. Open sets U containing x, and n there also exists an n2 in n such that whenever n is greater than or equal to n2, this implies that xn is contained in V for all open sets V containing y. But we know that the natural numbers are ordered, right? So since these natural numbers are ordered, I can always find a maximum between n1 and n2, right? So let n be the maximum between n1 and n2. Then as therefore if n is greater than equal to n, then it satisfies both these properties. That is, then xn is in U and xn is in V itself, right? Therefore, in this case, every neighborhoods of x and y will intersect at xn, right? If you negate the definition of Hausdorff, then every neighborhoods of U and every neighborhoods every neighborhood U of x and every neighborhood V of y must intersect, right? This is by negating the definition of Hausdorffness, and you can actually see it from here, because as n exceeds this capital N, so it satisfies both these properties. Then xn will be in every neighborhood U of x, xn will be in every neighborhood of V of y. So every neighborhood U of x and every neighborhood V of y, they will intersect at these points xn, right? So it contradicts the notion that the topological space we started with was Hausdorff. So it contradicts the assumption that x is not equal to y, right? So this cannot be true. Okay, they need to be equal to each other. Okay, right. Number 5 is that a subset K in X. Okay, so rather let me not use this notation. So K in X is said to be compact. Is said to be compact if every open cover of X, every open cover of K admits a finite subcover. That is, if you have an arbitrary collection of open sets whose union contains K, then there will be a finite subcollection of those open sets whose union will also contain K. Okay, right. And there are two more definition of compactness. This is the definition of topologically compact. There are I guess two more definitions of compactness. One is called the sequential compactness, that is every bounded sequence has a convergent subsequence. Every sequence has a convergent subsequence. And there is something called a Fréchet compactness itself, I guess. That is, every infinite set has a limit point. I guess there's some notion of a compactness like that as well. And over metric spaces, all the definitions of compactness are equivalent to each other. That is, if a sequence is compact, then it's also sequentially compact, then it's also Fréchet compact, and conversely. Okay, I'd rather not get into those discussions. Number 6, that a subset of the topology tau is called a base for the topology. Is called the base of tau if every element of tau, if every element of tau is some union of the elements of V. Okay. For example, recall that we have seen this in our real analysis course, that every open set is a union of open intervals, is some arbitrary union of open intervals. In fact, we can also restrict this to being countable as well. Every open set is a countable union of open intervals. Rather, let us not focus on that. Every open set is a union of open intervals, right? And the collection of all open intervals will then form a base of the standard topology, the standard Euclidean topology on R. Okay. The next definition is that a collection gamma of neighborhoods of a point P in X is a local base at P if every neighborhood of P contains a member of gamma. Okay. So this is the definition of what we call a local base. Clear? Number 8. If I have a subset of the topological space X tau, then Y is also a topological space. With respect to the subspace topology, so which we define as this. So this is the collection of all open sets U intersecting Y, where U is an open set in X. That is, the open sets in Y, they are of the form an open set intersecting Y. Clear? This is what we call the subspace topology. Okay. Okay. Now we will end this lecture with our introduction to a topological vector space. So let X be a vector space, tau be a topology on X, then X with tau is called a topological vector space. Now we already have a topology on it, we already have a vector space structure on it. So the only notion we need to define a topological vector space is acquiring some relation between the vector space operations and the topology. So X is called a topological vector space if, number 1, every point in X is closed. Okay. So every singleton set in X is closed. Number 2, the vector space operations are continuous with respect to the topology tau. Okay. That is, the what are the functional notions of the operations? So the map V cross V to V, which sends an ordered pair xy to x plus y, this should be continuous in tau, and the map from, sorry, I wrote it in a wrong notation, this was a highly abusive notation, V cross V to V, and the operation F cross V to V, which sends a scalar alpha and a vector V to alpha V, this should be continuous in tau. Okay. In this case, we say tau is a vector topology. how is a vector topology. Okay, so let me just briefly give the notion of continuity of these operations, and then we will end this lecture. Okay, so remark that if x1 and x2 are two elements from X, and V is a neighborhood of x1 plus x2, then by definition of continuity we know that the inverse image of V under this map, which sends xy to x plus y, should be open. Inverse image of an open set, sorry, I told it wrong. By continuity, by the definition of continuity in topological space, we know that the inverse images of open sets must be open. So if V is a neighborhood of this point, then V is an open set containing containing x1 plus x2. So the inverse image of V under this map, which sends the ordered pair x5 to x plus y, must also be open. So and V is a neighborhood of x1 plus x2, then there exists neighborhoods v1 v2 of x1 and x2 respectively, such that v1 plus v2 is contained in V. So this is exactly the notion of the inverse images of open sets being open under continuous maps. And the other remark for the scalar multiplication is that if x is in capital X, alpha is a scalar, and V is a neighborhood of alpha x, then how do we define it? Then for some r greater than 0, some neighborhood w of x, beta w is completely contained in V whenever beta is in the open ball centered at alpha of radius r. Clear? So just try to check. This is some sort of a non-trivial statement, but check that it abides by your usual notion. Okay. Okay. So let me end this lecture here. In the next lecture, we will be coming up with the other topics related to topological vector spaces.